Alright, part 2. And of course the paper's in the wrong place. There we go. Took the opportunity to look up the numbers. German Type 7C U-boat. 9.6 metres high with a 4.74 metre draft. 67.1 metres long with a 50.5 metre pressure hull length. 6.2 metre beam, 4.7 metre pressure hull beam. Surface displacement 769 tonnes, submerged displacement 871. Now this was what these days we would probably call a submersible rather than a submarine. It's a diesel boat that drove around on the surface but could dive for a while to avoid detection and to avoid having to fight, mostly because they're designed to hit things and then off in a hurry rather than get into prolonged battles like a battleship. The pressure hull is the thing that contains the engine, the instruments, the controls, the torpedoes, fuel supply, the batteries, the crew, they're quite important, the galley, and everything like that. Outside you would have floodable torpedo tubes in front and aft, or at least in front, and also the buoyancy tanks or ballast tanks, depending on your point of view, which allow you to vary your displacement. This is how this thing gets to dive and come back up. Pressure hull allows it to survive, and somewhere on that page it probably says how far down it's supposed to be able to survive. A couple hundred metres. And because it's steel hull rather than a canvas bag, it's not going to be compressed like a BCD. The pressure inside, or like an upturned boat, pressure inside it isn't going to increase vastly as you go down and drop sharply as you surface, which is a lot better for the crew. You can't scuba dive on compressed air down past 60 metres. Somewhere down there the partial pressure of oxygen gets so high that it becomes toxic and you pass out and die very quickly, very painlessly. Very expensively. Some poor sod has to go and get the body back. Floating on the surface, like if you took off the outer hull, if you just made it to the pressure hull, it would sink. As would, you know, a tank. If you threw that into the sea, how do you get a tank turret to drive around the sea with a tank motor powering it? You add a whole lot of displacement. You add this great big sleek steel hull whose sole job is to push water out of the way and create an air pocket which creates buoyancy, which supports all that machinery and the crew and the ammunition and everything else. In the case of most ships, that is kind of that shape. And you have hatches here which can probably resist, you know, a quarter of an atmosphere. In the case of a submarine, instead of having a lot of empty space here inside the ship with all its decks and so on, they have a very cramped inner space and they have their empty space stuck on the sides. This is your pressure hull. This is the outer hull, and it's open at the bottom. It has vent holes. This could seem crazy. You have holes in the bottom of your ship. If you're like this and you had vents at the top as well, the water would rush in, air would be displaced out of the top, and your vessel would sink. With a submarine, it's closed at the top, so that doesn't happen. Let me just make sure I'm on the page. Yes, I am. Good. So we have water outside the submarine, and also up inside between the pressure hull and the outer hull. So your water level outside could be somewhere up here, with the water level inside there. Well, water level in those spaces there. Now if you want to dive, you could just open holes here, have valves there like exhaust valves on a car's engine cylinder, let the air out, let the water in. That'll get you underwater fast, which is kind of useful in a, in a naval conflict situation. Anyone who's seen Das Boot will be familiar with the concept of the emergency dive, because there is a destroyer driving right at you and firing its guns in your direction. Or because there's an aircraft coming your way, trying to bomb you, or whatever else may go horribly wrong for a submarine. What that does is let the water come up here and fill this space, or partly fill it, pushing this air out. If you're losing this air, you're actually losing mass, but not much mass. You're also losing, well, in this sense, in the way Craig was describing it, you are adding this water to your ship, increasing its weight. From another point of view, you are losing that volume of air, decreasing your displaced volume and decreasing your buoyancy. Both come out to exactly the same thing. The density of the seawater minus the density of the air, multiplied by the volume of seawater that has replaced air in this tank, is an increase in the net downward force on your ship. And glug, down it goes. You don't want to go down forever, you want to stop at some point, maybe 150 metres. You would close these again, and you can pump air from this compressed air tank out into here. The air being less dense than water, it'll take up space at the top and drive the water level down, forcing seawater back out. This is not changing your weight at all if you're looking at the non-water part of the boat. The air is merely going from compressed in there to uncompressed here, but it is increasing your volume by whatever volume of seawater is driven out, which increases your buoyancy. Alternatively, if you include the seawater as part of the weight of the ship, it is decreasing your weight by the weight of the seawater that's pushed out minus, well no, just by the weight of the seawater that's pushed out. It's just decreasing your weight by that much, and you're keeping exactly the same displacement, so your net force changes in an upward direction. It goes from down to zero, or from zero to up, or even from slightly down to slightly up. And you would use enough air to push out enough water to get enough combined volume of pressure hull plus air in tanks to displace enough water to balance the mass of your boat and all its air, or to get enough to reduce the mass of water to the point in your tanks, to the point where that water plus your boat plus your air weigh as much as that water plus your boat plus the air are displacing. Either way, you can achieve neutral buoyancy with that. It has a bit of a problem, that same thing as the scuba divers, that as you go deeper, the pressure is increasing. So whatever volume of air you've got here is going to get squeezed smaller and smaller by the increasing pressure, which decreases your displacement, or lets more water in and increases your weight, whichever way you want to view it, increasing your net downward force and making you sink faster and faster. Serious risk. There is an obvious lower limit where the pressure in this tank equals the pressure outside. At that point you can't displace the water. If you open the valves, nothing's going to happen. Any lower than that, seawater will actually come into your compressed air tank. At this point, you're fucked. So at some point down there, somewhere down the bottom of the ocean, there is a depth from which the submarine, no matter how well it's built, couldn't possibly escape. Unless you have a pump as well as the compressed air. Unless you can put air into that tank more pressure than there is seawater pressure around you, you can't float. Maybe you could run the engines to max and point the nose up and drive upwards harder than your weight is pulling you down and get away. Maybe. Of course, if a scuba diver's air tank on his back can hold 200 atmospheres, it's reasonable to assume that that thing can hold 200 atmospheres. That's already 2 kilometres depth. Nobody works down there, right? Maybe 3 kilometres. How deep does the ocean go? Well, the ocean goes to 10 kilometres, but a lot of it is less than 2 kilometres deep. And really, naval battles, mostly take place on the surface, the submarine stuff mostly in the first 400 metres, so that's fine. More likely your pressure hull will fail before you get to the point where you don't have enough pressure to do that. However, you do have that issue of, as you go deeper, you get less buoyant. As you come up, you get more buoyant. So you have those fins, don't you? Front and back of the boat, you have wings. Maybe not quite that big, but you have wings you can tilt to push the nose up or down, or push the tail up or down as you go, and also rudders. Thus allowing you to drive your boat wherever the heck you feel like, rather than relying entirely on this. There is another approach to this you could take, which actually beats the changing pressure problem, sort of. Instead of having those air tanks and the compressed air, or as well as that, you could have on your submarine, bear in mind, modern submarines are meant to stay under for months at a time, U-boats for hours at a time. Yeah, one thing that came up, you would, if you were happily cruising at 50 metres and you wanted to go down to 100, you would pump the air from this tank into that tank, not vent it out. Because if you vent it out, you create a stream of bubbles on the surface, and U-boats are meant to be hidden. Anyway, you could have, on the side of your boat, front and rear, so that you can adjust buoyancy at the two ends separately and actually make it nose heavy or tail heavy or balanced. Tubes open to the sea at one end. Actually, it should be open to the sea at the inner end, I believe. Close that. And open to air tank at the outer end, each with a piston in it. This is just a thought here. See, I've drawn the pistons going on the dry side so that you don't have water pressure trying to get into your piston system where it goes through. But of course that means it's sticking off the end of the ship, so maybe your piston should go this way on the wet side. Also, you get more volume for less piston movement if the piston is on the wet side. Okay, redraw. Have a thing, something like that. With a piston for a pressurised chamber, so water can't go through because the pressure gradient is that way. Ha! With water in here on this side and air on this side. This way you could move the piston back and forth, and the position of the piston would control the volume of air and therefore control the volume of water, and control your displacement or your total weight, whichever you prefer. And then, as long as the machine that moves this piston is strong enough not to care about the water pressure increasing as you go deep, you get to take advantage of something that in GCSE physics you'd probably be told doesn't exist. That's a scary thought. I just agreed that teachers lie to you. That. Focus. That's something you might get told doesn't exist in GCSE physics. That is increasing density with depth in seawater. Now if you look along the top, you can see that, in grams per cubic centimetre, kilograms per litre, tonnes per cubic metre, they're all the same unit really, you're only going from 1.025 to 1.028. That is a tiny increase, very little compression happening, but it's there. And if you can control the volume of your fixed mass submarine, because it's not blowing bubbles, it's not dumping sewage into the water, it's not taking air in, it's staying at exactly the same mass. Nuclear sub. Oh, wait, does a nuclear sub stay at the same mass as it uses nuclear fuel? Yeah, near enough the same mass. it's converting some of it to heat, and that does get lost to the water. But it's pretty much a fixed mass, and you can control the volume of it, you can control its average density. If the water is increasing in density with increasing depth, down to, notice, 1 kilometre deep there, you can control, if you can control your ship's average density finely enough, you can put your average density just say there, and your ship will be neutrally buoyant at that depth. If you go any deeper, the water gets more dense, but your boat doesn't, and your boat bobs upwards. Go any shallower, you're going into less dense water, and your boat will become negatively buoyant and sink. So you could actually set a piston buoyant rather than inverted cup buoyant submarine to be neutrally buoyant at a particular depth, and it would stay there, which is probably kind of handy. It's also what happens with a helium balloon if it doesn't go high enough to pop. It's going to rise up and expand as it rises, but because the pressure is dropping, but be rising into thinner and thinner, less and less dense air. If it gets to the altitude at which it is neutrally buoyant, then it'll just stay there. It'll go up and down a little with the changing weather, but it'll stay at, roughly that altitude. Of course, your volume is going to change very slightly as you go down. Your volume is still going to decrease because seawater ain't the only thing that's compressible. So steel. Your entire submarine is going to get smaller. And you can demonstrate this one in the swimming pool, again, if you can swim. Get a balloon, a normal balloon, inflated, with a knot tied in it, full of air. Or partly full of air. Let's half inflate a balloon at sea level, take it up a mountain, and it will expand due to the decrease in air pressure. It will expand, That's a heck of an expansion because it's a cube expansion. What is the cube root of 2 anyway? Let me just check that. I think it's 26 by 1.26. 2 cube root. It is indeed 1.26. So if it gets 26% bigger that way and that way, it's doubled in volume, indicating a halving of the external pressure. If you take it into the swimming pool and pull it underwater, you can feel the buoyant force trying to push it back up, as if you've approximately equal to trying to lift that much water. But you can also observe that the balloon will get smaller and smaller as the water is squeezing it. Now, a steel pressure hull doesn't shrink that much, but it will shrink just a little. However, I think that would allow you to simply go, yep, I want to be neutrally buoyant at 150 metres, set it to 150 metres, float along there. You could even mark your depth on this, Why did this come up? It came up because some guy was, well, I wouldn't say arguing, blathering. Blathering is probably a good term for it. About submarines, saying that submarines prove the Earth is flat because if the submarine stays at a fixed depth in a flat ocean, it's fine, but if it tries to stay at a fixed depth in a curved ocean, it'll go out into space. This is clearly what cool hard logic would call bollocks, because it's set for depth. That is a depth. That is a depth. That is a depth. If you set it for that depth, it is going to cruise at that depth in between those other depths, like that. Because that's where that depth is. Depth is from the surface, not from some arbitrary straight line up here. Have I mentioned that the guy's an idiot? I probably should mention that the guy's an idiot. That didn't even go ding, come on. There we go. Because flat earthers are idiots. Not the best dinger, but a dinger.